Okay, so now we are going to discuss about the new chapter of thermodynamics, that is exergy and available energy. Okay, so exergy, what is exergy? The maximum amount of work that can be obtained from the system is known as exergy. See, exergy, available energy, availability, three are same. Okay, three are same, but in the some books it has been written that available energy is for a system which is operating under cycle, and availability is for the process actually, but three are same. Three correspond to the maximum work, whether he may ask available energy, exergy, or availability. Okay, three, it means that he is asking you to find out the maximum useful work, maximum amount of work, okay, from the system. Okay, availability is nothing but when the cycle system is undergoing a cycle, we maximum amount of work is known as available energy. Availability is system undergoing a process. Okay, this is the concept. Okay, so now what is dead state actually? System is said to be in dead state when it comes with equilibrium with surroundings. Okay, so generally, if you want to discuss about this thing, if you take one copper block at 1200 degrees centigrade, okay, generally we can extract work from the copper block. How we are going to extract the work? We are going to cool the copper block. Once we cool the copper block, we'll get the heat. Okay, copper block is cooled in the sense it will reject the heat, right? The rejected heat of the copper block we are going to utilize in the heat engine actually. Heat engine we are going to use, and we are going to get the useful work. Okay, when we cool that copper block. Okay, so suppose 500 degree copper block is there, then also we can we can get the work, useful amount of work. But when the copper block comes to the when it comes to the dead state, that is when it is in equilibrium with the surroundings, that is the temperature must be same, and each and every thermal equilibrium, mechanical, chemical equilibrium, each and everything must be same, right? Even pressure must be same. Okay, when it comes to be when it comes with equilibrium with the surroundings, we cannot extract the energy. Look, generally if the copper block is at room temperature, can we say that it has some energy? Yes, it has some energy. If the generally if the fluid, if you take the water at room temperature, does it has the energy? Yes, it has the energy. At 0 Kelvin, energy will be 0. Okay, entropy will be 0, internal energy will be 0, because temperature is 0 Kelvin. So each and everything will be 0. Generally, if you want to measure the entropy and enthalpy, you will give the water and it tells you to find out the enthalpy. We must take the one reference point, like absolute 0 reference point, and we are going to measure the, and we will measure the enthalpy and entropy of the water. Okay, we can easily measure the enthalpy and entropy of the water. That is the main thing. And what I was saying, ki, uh, yes, yeah. So air is at 40 degrees, there will be enthalpy once a period. Energy is there, but we cannot extract the energy. Okay, so atmosphere is the source actually. So actually, why we are not extracting the energy? According to Kelvin Planck's statement, there must be two reservoirs to do the useful work. Generally, we cannot produce the work by operating with the single source reservoir. We are not going to convert the same amount of heat into work. Okay, we must reject it into surroundings. It must operate in the source. There must be a sink, right? So atmosphere is the source. We are taking the energy. So where will be the sink? Where will be the sink? Okay, we cannot we cannot reject the heat actually. All right, we cannot reject the heat actually. So yeah, minimum two reservoirs will be required for according to Kelvin Planck statement. Okay, and if you take example of our body's temperature is greater than the atmospheric temperature, right? Greater than the atmospheric temperature, we are rejecting heat to the atmosphere, right? So when the body comes with the thermal equilibrium with the surroundings, then the person will die. When the person dies, will come with the come with thermal equilibrium with the surroundings. Okay, so if body comes to with the dead state, temperature will be same as the temperature of the surroundings. Okay, when you touch the body, you will feel the body is cool. Okay, body is cool, but the body will not cool. Body will be at room temperature itself. Okay, so due to the thermal conductivity, we are your heat your generally your body's temperature will be more when compared to dead body temperature. Okay, so when you touch the body, soon according to thermal conductivity of the body, you lose heat. Okay, you lose heat to him, because it acts as a sink, and you as a source. Okay, so generally temperature heat flows from higher temperature to lower temperature, right? So you feel cold because actually the heat is rejected from your body, okay, to him. That's why you feel cool. Same as the copper lock, you take the copper lock and pass plastic bottle, copper lock you can feel full because thermal conductivity of a copper lock is more than the plastic bottle, right? So you will lose your, when you touch the bottle, you will lose the heat from your hand. All right, that's why it feels cool. Okay, so we talked till dead state, right? So now we are going to talk about the available energy, derivation of the available energy. Okay, generally what is available energy? You know, the maximum amount of energy which we are, which we are, that can be obtained from a cycle is known as available energy. Okay, so that is the thing. According to second law, complete conversion of heat into work is not possible in a particular cycle, right? A minimum of heat must be rejected. The minimum of heat must be rejected. If an interviewer asks you that whether tell me why it is not possible to totally convert the heat into work, you can't tell the heat is a low grade energy and work is a high grade energy. Low grade energy conversion of low grade energy to high grade energy will be losses and all. You can't tell like this. Okay, you just tell it is the second law of thermodynamics. Okay, it is a second law of thermodynamics. I can't prove the second law, but while law cannot be violated, right? That is the that must be the answer. So maximum amount of work, what we are doing, we are focusing on maximum amount of work. Okay, maximum amount of work that can be obtained from the cycle. Our focus is on uh, that extraction of maximum amount of work. Okay, they were production of maximum amount of work. So if I supply q in amount of heat, so I must I must get the maximum work from that heat, and I must reject the minimum amount of heat. Okay, minimum as possible I must reject the heat. Okay, that must be my generally basic, focus must be on rejection of minimum amount of heat. That rejection of minimum amount of heat is known as unavailable energy. Okay, amount of heat that is the amount of heat that is that is available for conversion into work is known as available energy. Generally when I supply some amount of energy, to get the maximum amount of work, what I must do, rejection must be minimum. I must reject the minimum amount of heat. That minimum amount of heat which is rejected is known as unavailable energy, and the energy which is available for the conversion of work is known as unavailable energy. Okay, that is the thing. Generally there will be two conditions. When I tell you that to get the maximum useful work, then you must focus on 2 points. Okay, one point, the that must be a reversible cycle. Okay, because reversible cycle efficiency is greater than the irreversible cycle efficiency. Okay, you will get the maximum work in the reversible cycle efficiency, and which cycle has the maximum efficiency, that is the Carnot cycle. Okay, so with the help of the Carnot cycle we will discuss about the derivation of available energy and available energy. Okay, so that must be first thing. Next thing, generally I must reject the heat at atmospheric temperature. Okay, atmospheric temperature, that means rejection of heat must take place at atmospheric temperature. As you can focus on both these things, these two things are not possible. To get the reversible cycle, it is not possible, and to reject the heat, it is not possible. Suppose for example, if you take a bike, okay, bike silencer of the bike is there, right? Once you touch the silencer of the bike, once you touch the silencer of the bike, the silencer is heated, right? Silencer is heated. That means that you are not rejecting the heat. You are not rejecting the heat at atmospheric temperature. You are rejecting the heat greater than the atmospheric temperature. Okay, that means you are wasting the heat. Okay, that is the thing. So yeah, the point, loss of available energy tends to increase in unavailable energy. Okay, when the heat is transferred into the finite temperature difference. Simple, it is simple, sir. Generally मेरे पास food है. Okay, food है. If I eat the half of the food, then half will be wastage. No, that is the thing. Loss of available energy leads to loss of gain in unavailable energy within the when you transfer the heat between the two finite temperature difference. Okay, this is the thing. But now we are going to prove that if I supply q in amount of heat, that q in amount of heat will be either available energy or either unavailable energy. Some of available energy and unavailable energy. This we are going to discuss. Okay, with the help of the Carnot cycle. Okay, so first of all, let's take the Carnot cycle. First of all, what I told you, the reversible cycle must be it must be a reversible cycle. So what is the efficiency of reversible cycle? 1 minus TL by TH, which is also given as Q in by QH by W. Okay, we will take QH because writing of QH is very very simple. Q in IN QH, directly you write QH. Okay, so QH by W by QH. Okay, so W here will get as QH into 1 minus TL by TH. Okay, so this is the work which we are getting from the Carnot cycle, maximum work. Okay, so this is not the maximum work, this is the work, useful work. Okay, so sir, to maximize the work, what is the next condition? That I must reject the heat to the surroundings at T0 temperature. Okay, so W maximum is given as equal to, or available energy equal to, QH into 1 minus T0 by TH. Okay, this is the formula. Okay, now what is unavailable energy from the diagram? That is the minimum amount of heat that is rejected, right? QL amount of heat is rejected, right? So uh, QL amount of heat is rejected between the temperature T0 and DS. So I can write it as that area QL equal to, what is the area, sir? Area is T0 into DS. Area is T0 into ds. Okay, so from available energy I can write as Q in QH minus QH in by TH into TL. Okay, QH by TH is actually TL by QH by sorry, wait, QH T0 can be written as T0 equal to QH by DS. Wait. Okay, similarly I can write QH as QH, how to write QH from the area below the curve, right? T0 TH. Okay, QH can be written as QH can be written as QH equal to T0. From here I will come to know that A equal to QH. Okay, first of all QH minus QH by TH can be written as DS, right? T0 DS. What is T0 DS? T0 DS is unavailable energy. Okay, Q in equal to available energy plus unavailable energy. This is the derivation. Okay, so two things you must need to focus, that the cycle must be reversible, perfectly reversible, and the next you must reject the heat to the atmospheric condition. Okay, so now we are going to discuss about the last point, that is if we add QH amount of heat, right? So there will be that energy is utilized either in converting into useful work, or that energy is wastage. In other words, QH will be equal to available energy or unavailable energy. If available energy is decreasing, then increment in unavailable energy. So now generally in an actual cycle we are going to discuss the loss of, generally we mentioned that it is Carnot cycle, right? It was Carnot cycle. In the Carnot cycle, the system temperature and the source temperature both are same. If the system and source temperature both are same, then the heat transfer will not take place. Okay, heat transfer will not take place. Okay, heat transfer due to finite temperature difference is treated as perfectly reversible. So the Carnot cycle is perfectly reversible. But generally, the heat transfer to take place, the system temperature must be less than the source temperature, right? So we took the T1 dash as a source temperature. If we are changing, the cycle becomes irreversible. If the cycle becomes irreversible, then there will be entropy generation. Due to the entropy generation, the entropy of the system is going to increase. Okay, all right, that is the thing. So now we are going to if the entropy generation is increases, Tn is decreases, Qin is same. Okay, QH is same. Notice here that QH is same. If we are decreasing the temperature, QH also decreases, but we are considering that QH is also same. Wait, give me. Skip. Alright, yes. QH is also same. So now there if you notice the diagram, generally the DS entropy will increase, right? Entropy will increase. Now the all things are changed. Available energy is changed and available energy is changed, and the extra cycle, extra part, blue part is known as loss of available energy. If the available energy is lost, then there is a gain in unavailable energy, that is increment in unavailable energy, that we are going to find out. Okay, in the actual cycle, if there is a, if we are going to decrease the temperature of the system. All right, so it is given by T naught into ds dash minus ds, right? This is the concept. Now ds dash can be written as t1 dash qh by t1 dash minus ds can be written as qh by t1. So qh, if you take common, then it will come uh, it will come as hmm, it will come as t naught times qh into t1 dash minus t1 by t1 dash. Okay, this was the loss of available energy. Now if you want to find the available energy, then what we are doing, we are simply we can find by using the area of the diagram below, right? Now area of the diagram, like qh into 1 minus t naught by t1 dash. This is available energy. What is unavailable energy? That is t naught into ds dash. Okay, this is unavailable energy. T naught into ds dash. What is loss of unavailable energy? T naught into ds dash minus ds. Unavailable energy. Loss of available energy is equal to loss of gain of unavailable energy. What is the gain of unavailable energy? So why you are not directly finding the loss of available energy? Loss of available energy can be found out in one more way, right? So we can't find it. It will become complicated. So we are finding loss increment in unavailable energy, that is given by the blue area. Okay. All right, so we discussed about the loss of available energy and gain of unavailable energy, right? We discussed it. Now question number 4 and question number 5. So generally the mistake which I did in the question number 5, the question number 4, it was easy, okay, but question number 5, the first mistake was generally I didn't read the whole question. Okay, this was my first mistake, because he asked about he gave delta t. And next mistake which I did was, generally what I did, I took drop in Kelvin. Okay, I converted 50 plus 273, and I minus 50 plus 273, and I added to th. Then I calculated the W max, but that was wrong. Next mistake which I did was, I tried to manipulate the data, okay, without knowing the concept. That was my mistake. So generally know the concept first of all. What is the concept? Then do the manipulation. Then don't do the manipulation with the data to get the answer. Okay, you just keep calm and understand the question first of all. When you understand the question, then you will come to know that what question he has provided. So based upon that question you can answer it. Okay, so he has given the 50 degree centigrade temperature drop. It means we can take 50 Kelvin. Okay, so first of all it will be drop in th. Okay, because system temperature is less than the source temperature, right? 50 degrees centigrade. And also we are not rejecting into the atmosphere, we are rejecting to the to the temperature which is 50 degrees centigrade greater than the atmosphere. Okay, difference he has provided delta t. He didn't provide the tf value, he provided the difference, right? So difference either you can take in Kelvin or degree centigrade. Okay, so that you will get W work. Okay, so to calculate the loss, first we have to calculate the unavailable energy minus useful work, right? So how you can calculate the loss of available energy? Okay, loss of available energy. So you have to calculate available energy first. So how to calculate the available energy? Here I did a mistake again, that I confused them with the concept. Just first of all, what is W? Actually W is available energy. I confused there. Okay, W is available energy. What? W is available energy when we are rejecting heat to the ambient conditions, that is T naught. That is available energy. That is the maximum useful work. What is the maximum work for the cycle? It is given by Q in my into 1 minus TL by TH. TL by TH normal work. Okay, maximum work. actual work, but maximum useful work what can be calculated by rejecting it to the sink. Okay, just remember the concept, just go with the concept. This was the part A. Okay, I did 4 to 5 mistakes in this one thing. Okay, manipulations of data, and at last delta t in delta t, and you know uh, at last calculating of the available energy. So next thing, yeah, this concept I don't know first of all. Okay, I studied what I forget. If you forget, then it will be fresh for you. Okay, all right. So generally he has given the linear, the temperature will decrease, right? There will be source temperature will decrease to 550, sink temperature will increase to 50, but there is a linear variation. Linear variation in the sense, if you draw the cycle looks like that which has given the nodes. Okay, so how to calculate available energy, how to calculate maximum work, how to calculate loss of available energy in this thing. So generally this is not this is linear, but we have to convert it into Carnot. Okay, if we convert it into Carnot, we can easily find by using the diagram. Okay, so to convert into a Carnot, we have to take the mean value, because there is a linear variation. What is the mean value, sir? Mean value in the sense, what is the maximum temperature? 625 625 plus 625 divided by 2. Okay, you will get, wait, okay, 675 plus 625 divided by 2, right? It is right. You will get you will get the mean value. Or you can do one thing, you just to calculate what is the difference, actually 50 by 2, that is 25. You add 25 to 675 is 6, you subtract 25 to 675, or you add to 625. Okay, if you add to 625, you will get 650. That is the temperature at which the heat is heat is q in. So you calculate W work and W maximum work, that is same. Okay, that W maximum, that is not same actually. That is 1 minus T naught by TL. Here TL is 650 actually. Okay, so from here you can calculate the loss of available energy. Okay, so this is the thing. So continuation of the availability, we studied till two problems we solved, right? So now we are going to continue the availability. Okay, so generally for the process, we need to find the what is a useful work. Okay, what is a useful work? So how to find the useful work? We are going to derive the equation. Okay, according to, for the closed system, we are going to derive. Okay, dq equal to dq for the system will be equal to du for the system, ds dw for the system. So dw for the system we are going to get, okay, dw of system equal to minus dq of system plus dq of system. Dq of system will be equal to minus dq of surroundings. Dq of system equal to minus dq of surroundings. Dq of surroundings again can be written as d naught into ds of surroundings. Ds of surrounding can be written as minus ds of system. Okay, this is the loss. Okay, generally it's the surrounding entropy. If the surrounding entropy is decreasing, generally where does this came from? So dq equal to ds of system plus ds of surroundings must be greater than or equal to 0. What is this? This is the second law of the thermodynamics for the process, right? So for the if it is a reversible, then we will take equal to 0. So ds of system will be equal to minus ds of surroundings. If the entropy of the surroundings is decreasing, then the system entropy must increase. Okay, if you supply the heat, from the surroundings, then surroundings dim, it is minus dq, right? So same heat must be uh, utilized by the system, that is dq of system. Okay, that is those two equations, you just know those two equations. Okay, so dw of system equal to minus d of system minus of minus plus t naught into ds of system plus t naught into ds of system, which I derived. So derived this like minus t naught into ds of minus of ds of system. Okay, so derived this one, but I derived for the simplification purpose plus t naught into ds of system. Okay, so this is the equation generally. Now we are going to integrate. If we integrate, what we will get w useful work, w max, we will get maximum work. Okay, we will get the maximum work. So we'll get the maximum of u1 minus u2 plus d naught into s2 minus s1 we'll get, okay. So s2 minus s1 plus s2 minus s1, this I derived the equation, okay. This will be in kilojoule. For example, if you want kilojoule per kg, then we will multiply with mass, okay. This is the maximum work which is going to obtain from the system. This is the maximum work which is going to be obtained from the system, okay. Suppose for example, generally what happens, generally if there is this reject container is there, okay. Reject container is there. Now generally the container is at room temperature and pressure is 1.4 MPa. Can you tell me what is the work done will be zero, because it is a closed container. If you expand, it is a constant volume expansion process, right? dW will be zero, but availability will not be zero. Availability is the maximum work which is obtained from the system, okay. System से work कितना possible है, that tells you availability. मतलब how much the potential, that tells you the availability. It is same as generally if students are preparing the gate examination. So if one has the potential to crack the examination, then we can say that he will crack the examination. Whether he may crack or he may not crack, he may do that work or he may not do. But we can say that yes, he has the potential to crack the examination based upon his qualities. Okay. Similarly, availability tells you that कि सिस्टम के पास जनरली आपका से प्रेशर 1.54 MPa है. It is not atmospheric pressure. Temperature is atmospheric, but if we expand again the system, there will be work can be obtained from the system, but dW will be zero, okay. So what is the maximum? Now next thing also, the next one of the important thing is that कि जनरली अपन क्या करते हैं, डेथ स्टेट तक उसको एक्सपांड करते हैं, ओके. डेथ स्टेट तक अपन एक्सपांड करते हैं. So availability will not be zero. Might be बोलना भूल गया. So generally if there is piston cylinder assembly, then if you are going to if you are expanding, they will get some work, right? Work is done by the system during the expansion, but generally expansion work हो रहा, generally surrounding में compression work हो रहा, okay. Surrounding pressure is constant, right? P atmospheric pressure. Then that much work, there will be loss of work, okay. There will be loss of work, right? Expansion, if we expand the system, then the atmospheric compressing, okay. We cannot utilize the whole work, okay. But because some work is, if I get 500 kilojoule in the expansion process, that means that 500 kilojoule is cannot be utilized. अपन फर्स्ट लॉ सेकंड लॉ तक क्या पढ़े थे, जनरली W निकाल रहे थे अपन, dW, dQ, du, okay. So we are finding the dQ. It is a maximum work, right? But maximum work is not equal to useful work. Maximum work is different, useful work is different. Maximum work is different, useful work is different. Availability is different. Availability is nothing but generally maximum amount of work which you are getting from the system, okay. If we do the things up to dead state, okay, system in a cycle. So yes, by utilizing work, okay. So generally क्या बोल रहा था मैं, availability maximum amount of work which can be obtained from the system. If you want to get the maximum, then cycle must be reversible. Cycle must reject, we must reject to the atmospheric temperature, okay. That is a dead state. Till dead state, how much work is maximum work is going to be obtained from the system is known as available energy, right? So what is the work which we found? That is not the maximum work, okay. Maximum work is available energy work, okay. So and we derive for the maximum work for the process, that is W will be equal to u1 minus u2, because it is my ball minus u1 minus u2 plus T naught into s2 minus s1, right? T naught into s2 minus s1. यहाँ पे नेगेटिव आता, नेगेटिव अंदर चले जाता, alright. So entropy decrease, surroundings entropy is increase, alright. So क्या डिस्टर्बेंस है भाई. So work is we, we are expansion work. Suppose for example 500 kilojule आ रहा था अपने को expansion में. Okay, when the system undergoing constant pressure process or isothermal process, expansion work अपने को आ रहा था. Suppose 300. That 300 is not the useful work. Useful work is different, right? 300 is not the useful work. Okay, so useful work will be equal to maximum work which is going to obtain minus work done by the surroundings. Surrounding will do some work. Okay, surrounding will do some work on the system. Okay, so it will, to move the piston we need to overcome some work, right? It is expanding, it is compressing, like P into V naught minus. अब यहाँ से एक डॉट आता कि सराउंडिंग का एक्सपेंशन कैसा फाइंड करता है कि V naught सराउंडिंग हो तो सराउंडिंग एक्सपेंडिंग. सराउंडिंग का एक्सपेंशन वर्क नहीं हो, वॉल्यूम नहीं हो. जनरली पिस्टन का ही वॉल्यूम्स है वो. ठीक है, पिस्टन इज का ही वॉल्यूम्स है. सो वी विल सॉल्व वन प्रॉब्लम बेस्ड अपॉन दिस. ओके, डोंट वरी. Availability for the open system. Same availability for the open system. H1 plus Q equal to H2 plus W. इसको मैनिपुलेट करके W is for the open system will be equal to H1 minus H2 plus T naught into S2 minus S1. Okay, this is again, but यहाँ पे है ना useful work. This total work which are getting, this is the useful work. Maximum work is useful work because there is no any, if there is a resistance heater, there is no resistance by the surroundings, right, in the open flow. So hence this is the maximum useful work. Okay, psi 1 function values देते pi 1. Okay, pi 1 कैसा देते बोले तो जनरली pi 1 minus pi 2 ऐसा. स्टेट अवेलेबिलिटी इन स्टेट 1, अवेलेबिलिटी इन स्टेट 2 ऐसा देते हैं. सो pi 1 इक्वल टू ऐसा देते हैं U1 minus T naught S1, T naught S1, U2 minus T naught S2. T naught S1, T naught S2 ये हो गया, प्लस P naught V1 प्लस P naught V2. ओके, दिस इज pi 1 minus pi 2 ऐसा देते हैं. सो जनरली इफ देयर इज अ रिजेक्ट कंटेनर, आई टोल्ड यू, आप अगर से वेलोसिटीज वगैरह दिया हुआ है देन यू कैन क्वेश्चन का लेंथ इंक्रीज हो जाता, बट यू कैन फाइंड H1 minus H2 plus C1 square minus C2 square by 2000 plus GZ1 minus GZ2 by 1000 plus वो T naught S2 minus S1 plus T naught S2 minus S1 और minus T naught S1 minus S2. both are same. Rigid container is there, atmospheric condition है, pressure ज़्यादा है, then tell me what will be the W? W will be 0, no doubt, but availability will not be 0. Availability maximum useful work which is obtained from the system if we if you expand the system to the dead state. Alright, so W will not be 0. How to find the useful work, sir? How to find the useful work? So how to find the work? First of all we need to find the availability at state 1, right? Availability at state 1, we are expanding system to the dead state, right? So now the equation will be U1 minus U2 plus T naught into S2 minus S1 minus P naught into V2 minus V1. अब V2 फाइनल कंडीशंस क्या है, सिस्टम की फाइनल कंडीशंस है 120. सो V2 we must find out P2 V2 minus P2 V2 equal to MR T2. From here we can find out V2. So T2 is 25 degrees centigrade, that is 298, and P2 is 100 kPa. Okay, you can expand it to the और टेम्परेचर भी ज़्यादा है 175, सॉरी 175, ये टेम्परेचर भी ज़्यादा है. सो ये है MCV dt. अब T2 क्या है, T2 is 25, T1 is 175. okay, P2 is 100, P1 is 1.4 ऐसा. okay, all these things you need to take care of. what is P1, what is P2, what is V1, what is V2, what is P0. okay. and at last P0 into ये है 1.4 into नहीं है 1 P0 into V2 minus 7. okay, this is what. all right, सिंप्लिसिटी के लिए मैं नोमेनक्लेचर्स लगा रहा, बट यू कैन यूज 0 सो दिस इज द कॉन्सेप्ट. बट जनरली ये हो गया अवेलेबिलिटी एट स्टेट 1. जनरली इट हेल्प्स यू फाइंड आउट द अनअवेलेबल एनर्जी फाइंड आउट करो बोलता हूँ. दिस इज अवेलेबिलिटी एनर्जी एट स्टेट 1 इन शेड्यूल. जनरली when the system comes to the at 25 degrees centigrade, but what will the pressure at 25 degrees centigrade? You must look at the pressure. okay, when you look at the pressure is 928 or 927 or something kPa. so अगेन वी कैन आई कैन एक्सपेंड इट टू द एटमॉस्फेरिक कंडीशन. एटमॉस्फेरिक कंडीशन तो आए नहीं, इसीलिए मेरा अनअवेलेबल एनर्जी भी ये होता. ओके, डिफरेंस बिटवीन दिस टू is gives you unavailable energy. So again I am going to expand. Now I am going to take the conditions. Okay, t naught t1 t naught t1 t naught equal to 25 equal to t1. Cool. t naught equal to t1 equal to 25 degrees centigrade. समझदार है. t naught equal to t1 equal to 25 degrees centigrade. But p1, what is p2? p2 I am going to find out. So p2 से p1. अब p1 is जनरली आप टर्म्स कैंसिल हो जाते हैं जनरली. अब बचता क्या मेरे को वो बचता. अच्छा, यहाँ से ds की वैल्यू कैसा लगाना है, एंट्रोपी की वैल्यू s2 minus s1 दिया. सो यू कैन अप्लाई दैट इज cp log p2 by t1 minus r log p2 by t1. ऐसे ही लगा दे बस है. सो ये इक्वेशन लगा दे बस है. सो m डॉट m इंटू एम सी पी डी टी एम सी वी डी टी एंड आगे m लगा m m डॉट लगाए. तो m डॉट क्यों लगा, क्योंकि अपने को किलो जॉल पर केल्विन में आना है. दैट विल बी इन किलो जॉल पर के जी. इफ यू मल्टीप्लाई विथ 1 विल गेट किलो जॉल पर केल्विन. ओके, so this was the thing. Okay, next 11th question. 11th question में generally how to find the available and ये copper block दिया था 1200 degree centigrade Kelvin something. We expand that copper block, that energy is used in in that Q in we are going to use find the available energy and available energy so on. It tells you to find. Okay, all right. So how to find? First of all, find the Q in. Q in will be mc delta t. How much heat I can get from the copper block. Okay, next utilize that Q in in what will be unavailable. First of all, find the unavailable energy, because Q in equal to available energy plus unavailable energy, right? Unavailable energy is T naught into ds of system. ds of system will be equal to T minus ds of surroundings, right? This is the thing now. So minus ds of the surroundings. So minus of you will get minus of that T naught into minus of ds of system. How can you find that? Using entropy principle, we simply find out mc log T2 by T1, right? T2 by T1. We are expanding to the till the dead state, so we will get one energy. So unavailable energy it will be equal to Q in available energy will be equal to this minus this plus that. Q in equal to available energy plus available energy plus unavailable energy is Q in, right? Available energy is equal to Q in minus so we will get the thing. Okay, next one of the important concept that irreversibility. What is irreversibility? There are certain confusions, right? So available energy आ गया, unavailable energy आ गया, loss of available energy आ गया. ठीक है, loss of available energy is unavailable energy. ठीक है, loss of available energy आ गया. Generally irreversibility आ गया, maximum work, useful work maximum work आ गया, useful work आ गया, actual work आ गया. ठीक है, इतने वर्क्स है, इतना ये तो लिटिल बिट ऑफ कन्फ्यूजन, राइट? बट while solving the problems you can overcome all these things. Irreversibility, Q in if you supply Q amount of heat, according to us the heat cannot be converted into work, and for a cycle so but there is a rejection. We must reject around use second law Kelvin Planck statement. There will be two reservoirs, right? We must reject some amount of heat. If we don't reject, the cycle will not work. Okay, for the process also we can expand it to del state, but we are not expanding it to dead state, right? We are there will be loss of work. So for the process also only up to we are going to expand up to dead state, but after dead state energy is also available. If we take this water, if we expand this water, then there will be energy. we cannot utilize that energy. Okay, अवेलेबिलिटी का लिमिट है डेड स्टेट तक, बट डेड स्टेट के बाद भी एनर्जी अवेलेबल है, राइट? एनर्जी है, बट एनर्जी कांट बी यूटिलाइज्ड. ओके, so that is the thing. Even cannot complete conversion is not possible. Even cannot complete conversion is not possible. There must be rejection. Okay, there must be रहता एनर्जी कैन बी. ओके, सो सपोज एग्जांपल बोला था 10,000 रुपीज़ है, कल करंट है 4,000 रुपीज़, 6,000 रुपीज़. So 4,000 rupees is unavailable energy. Okay, that energy is very important. You must reject that energy. Next, one of the most important concept मेरे दिमाग में आया अभी कि according to second law of thermodynamics, complete conversion of heat into work is not possible. Okay, complete conversion of heat into work is not possible. The cycle will not work. Similarly, in order to maintain, order to maximize the work, generally, if the student studies roughly 16 hours, then there will be losses will take place. Then the cycle will not work. You must give some gaps. So generally, रिजेक्शन 5 आधे घंटे में 5 मिनट रिलैक्सेशन कंपलसरी है और साइकिल टू टेक्स प्लेस. क्योंकि आप कर सकते बंदा नहीं काम कर रहा, नहीं दे रहा 5 मिनट भी बोले तो विल नॉट बी सक्सेसफुल. दैट इज द थिंग, राइट? ऑलराइट, सो जनरली अगर से 6,000 में से अगर से हम 5 रुपये दोस्त को दिया बोले तो दैट इज़ द लॉस ऑफ वर्क. दैट एनर्जी इज़ अवेलेबल, बट एनर्जी इज़ अवेलेबल, तेरे पास है, यू कैन गिव द वर्क. सपोज फॉर एग्जांपल आधे घंटे में 5 मिनट ब्रेक लिया, आफ्टर 30 मिनट्स यू टुक 5 मिनट्स ब्रेक, बट इन द 30 मिनट्स ऑल्सो यू आर टेकिंग वन ब्रेक. दैट इज़ लॉस ऑफ वर्क. दैट इज़ नोन एज irreversibility. Alright, that is irreversibility. Actually diagram गलत डाला, ठीक है? क्यों? इन देयर विल बी अवेलेबल एनर्जी, अनअवेलेबल एनर्जी. अवेलेबल एनर्जी में से निकल गया थोड़ा हिस्सा. दैट इज अवेलेबल एनर्जी. अच्छा, अवेलेबल एनर्जी में से हिस्सा कटा गया. अवेलेबल एनर्जी इज मैक्सिमम वर्क, उसमें से हिस्सा कटा गया. नाउ इट बिकम डब्ल्यू एक्चुअल वर्क. ओके, so that जो red हिस्सा है that is irreversibility. Okay, I think you understood this concept. So continuation of irreversibility. Okay, so we talked about the irreversibility, right? So what is irreversibility actually? So first of all, if I supply the Q in amount of heat, there will be an available energy and there will be unavailable energy, right? The energy which is wastage, that is unavailable energy. Inside the available energy, if I am wasting some energy, that is known as irreversibility. Okay, this we derived using by using that Carnot cycle. Okay, loss of available energy, which is increase in unavailable energy. Loss of available energy is known as irreversibility. Okay, so different types of work: maximum work, reversible work. These two are same. Okay, this denotes the availability. So while solving the problems, I will discuss in the analysis. Okay, so how to find these works? Okay, useful work is actually useful work is different. Okay, maximum work, from the maximum work, how much work we are using, that is useful work. Suppose for example, if I told you yesterday that some mass is there, mass of in a volume some mass is there, right? So I am going to expand that the pressure was 1.4 MPa and the temperature was room temperature, right? So I can expand it, right? So I can get the work. So generally, if I expand, suppose for example, if I expand the piston cylinder assembly, suppose for example, then the surroundings will compress, right? So surroundings have some constant pressure, and it will provide the do the work on the system. Okay, do the work on the system. Here work done by the system. So the difference between these two gives you the useful work. Okay, that is the useful work. Next, actual work. What is actual work? Actual work is we find the actual work, right? In the second law, Q in by W equal to that 1 minus TL by TH. This is the W is the actual work. So in the SFE equation we find the actual work. So actual work is different, reversible work is different. Okay, and useful work is different. Okay, these are the three cases actually. So let us continue how to find the irreversibility, how much irreversibility is there. Okay, irreversibility is, actually I told you that is loss of available energy. Okay, so rate of according to Gauss-Stodler theorem, rate of loss of availability or rate of increase of irreversibility is directly proportional to the rate of universe. All right, so this derivation we will see. Okay, I is irreversibility is directly proportional to delta S of universe. Irreversibility is directly proportional to delta S of universe. Delta S of universe can be written as T naught ds of universe. Okay, all right, so generally if you look at the derivation dq equal to ds du of system dw of system, and dw of system can be written minus du of system dq of system. Dq of system can be written minus dq of surroundings, right? So w actual will be equal to du of system minus uh, minus T naught ds of surroundings. So dw of reversible, how can we write? Minus du of system plus T naught ds of system. Okay, so from here we'll get entropy dw dw reversible minus dw actual gives you that how much energy is lost, that is how much work is wasted, that is irreversibility. Okay, that is given by T naught ds of system plus T naught ds of surroundings. If you take T naught common, ds of system plus ds of surroundings is ds of universe. Okay, this is the concept. So next we will talk about loss of work in the pipe flow due to friction. Okay, in the pipe flow, that it is a conversative force field. Okay, z1 head is same, q is 0 because it is insulated, w of control volume is 0, and c1 is equal to c2. So if you apply the Bernoulli's equation, we come to know that p1 minus p2 is greater than 0. If it is greater than 0, so I must add certain fraction, right? I must add the losses, where delta p is known as head losses due to friction. Okay, so delta p can be written as p2 minus p1 minus p2. Okay, so if I apply the SFE, so I will get h1 enthalpy h1 equal to h2. So TDS dh equal to minus VDP. So from here ds of system, if you want to calculate, we are calculating the entropy of the universe. Once we calculate entropy of the universe, why we are calculating? Because if we find the entropy of universe, then if you multiply with surrounding temperature, then we will get irreversibility, loss of work in the when the life is flowing through friction. So in order to find the entropy of the universe, first of all we need to find the entropy of the system plus surroundings. Entropy of the surroundings will be 0 because it is insulated. So what will be the entropy of the system? So to find the entropy of the system, we are going to towards the equation T naught into T ds equal to h dh minus vdp. Dh is 0, vdp. So ds equal to minus v by t dp, mr by p into dp. Integrate it, you will get entropy of the system minus mr log p2 by p1. And here p2 can be written as 1 minus p1 minus delta p. So 1 minus delta p by p, it is in the sense log 1 minus x. So if we expand, we are neglecting higher terms, we will get mr delta p by p1. Okay, mr delta p by p1, not log. Okay, this was the equation. So next the final topic, not final, but after this one topic is there. So second law efficiency. What is second law efficiency? Generally we can't compare the two cycles by using the efficiency. Suppose one cycle efficiency is 50%, another cycle efficiency is 60%. We can't compare, right? So if mileage is first cycle mileage is 50 km, for second cycle we by the conditions we can't compare the cycles. All right, we can't compare the engines because generally Luna's mileage is very more, but if you avoid the load on the Luna, then the efficiency will decrease. Okay, that is the thing. So based upon output, based upon input, we cannot but unless we know we don't know the working conditions, so we have to compare it with the first law efficiency. Generally we are going to compare it with the Carnot efficiency. Okay, so efficiency of reversible by actual by efficiency of irreversible give you maximum efficiency. Suppose efficiency of topper is 0.9, so if you 0.8 efficiency, then you will get overall efficiency. As in the gate examination they will do, okay, they will give you rank based upon topper's marks. Okay, if you got 100 marks, they will not give you first rank, but based upon the toppers, if the topper gives 92 marks, then he will be the one give you as given. So relatively to the topper, the ranks has given. All right, so similarly second law efficiency is actually used to compare the two cycles, two engines. Alright, so after solving the problems, basic problems, in the one problem the concept was we must not add q while solving the actual work. Okay, all right. So maximum work from an engine. If the engine is working, what you they see, there are three conditions actually. If there are two reservoirs means temperature is constant, so we can find the maximum work by using the equation Q in W equal to Q in 1 minus TL by TH. Okay. If the temperature is varying, okay, suppose for example, if there is a copper block temperature is 200 degrees centigrade. If we expand, we use that we are going to use it by for for conversion into work, right? So for that thing we cannot use the equation because that is final temperature body, right? So to find it, we must find the delta S of universe. Delta S of universe system plus surroundings. System surroundings is zero because delta S of universe of system plus surroundings, right? So system, what is a system? System is a copper. So what is a copper efficient formula for the copper? uh, mc 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 log t final by t initial. This was the thing, okay. And plus that, what about that reservoir? Q minus W, because for maximum work the cycle must be reversible. For the reversible cycle, q in q h will be equal to q w minus q minus w, qh minus w qc ql. All right, so from here we are going to get w maximum work, okay. But w actual we can find, so for using first law, this was the thing. But if the two final temperature bodies are there, so generally how first of all we must find the equilibrium temperature and we must find the delta S of universe. Delta S of universe is 0 for the minimum power, minimum work output, that will be maximum reversible work, that will be equal to ds of systems. ds of system, first to calculate ds of systems, okay. So if it is a replaced with gas, it will replace with a gas equation. If the gas, you will give the gas will be constant. If gas will be constant, then we will get the same equation, okay. This was the thing.